Hi, I'm Miss Hall.
Hi, I'm Ethan, and this is 67.
Recursive and explicit rules in arithmetic and geometric sequences. Do you want to say hi?
Hi, I'm Miss Active.
Evaluating recursive rules. So far in this chapter, you have worked with explicit rules for the nth term of a sequence, such as, and they give an example of an arithmetic explicit rule and a geometric explicit rule. An explicit rule gives a sub n as a function of the term's position number n in the sequence. In this section, you will learn another way to define a sequence by a recursive rule. A recursive rule gives the beginning term or terms of a sequence and a recursive equation that tells how a sub n is related to one or more of the preceding terms. We see recursive rules in example 1, and directions are to write the first 6 terms of each sequence. Okay. So here we're given the 0 term. So I can write the 0 term is 1. Then we're given the recursive rule. You'll notice that the rule is in terms of the preceding terms. Here's what I mean. Let's find a sub 1. A sub 1 is going to be a sub 1 minus 1 plus 4. See, anywhere there was an n, I put a 1 in because I'm looking for the first term. A sub 1 minus 1 is just a sub 0 plus 4. A sub 0 we know is 1. We were given it. Plus 4 equals 5. Okay. So 5 is term 1 in this sequence. For the second term, we'll do a sub 2 equals a sub 2 minus 1 plus 4. A sub 2 minus 1 is 1 plus 4 equals, well, a sub 1 is 5. It's the term right before. Plus 4 equals 9. So term number 2 is 9. Now for the third term, a sub 3 equals a sub 3 minus 1 plus 4 equals a sub 2 plus 4. A sub 2 is 9 plus 4 equals 13. That is the third term. At this point, you might be able to tell that the sequence is just adding 4 to the previous term. Right? I can speed this up. A sub 4, I know it's going to be the term before a sub 3 plus 4. A sub 3 is 13. 13 plus 4 equals 17. The fourth term is 17. I've run out of rule, but I run out of room, but I see the rule is plus 4. So I've got the first, second, third, fourth. If I add 4, I'll get 21, and then 26. 5, 6. And now I've got the first 6 terms of this sequence. Example 1b. Now this is written more in function notation. So we are given f of 1 equals 1. So we're given the first term. The first term is 1. The recursive formula is next, and I'm going to start by finding f of 2. I've already got the first term. Don't need to find it. So f of 2 is going to be 3 times f of 2 minus 1, which is 3 times f of 1. 3 times, well, f of 1 we were given is 1. So this is 3. F of 2, or the second term, is 3. Now to find f of 3, that is going to be 3 times f of 3 minus 1. Right, my n here is 3. And that is 3 times f of 2. And f of 2 is 3. So this is going to be 3 times 3 equals 9. term number 3 is 9. Maybe you see the pattern now. F of 4 equals 3 times f of 4 minus 1, which is 3 times f of 3, which is 3 times f of 3, is the term right before, that is 9. 3 times 9 equals 27. So my fourth term is 27. And so you can see what's happening is we're just multiplying every term by 3. This is an example of a geometric sequence. And I need my fifth term, which is going to be 81. I just multiplied 27 by 3. And then my sixth term is going to be 81 times 3. So that is going to be 243. Yes, 243. And here I have the first 6 terms of the sequence. Example 2, writing recursive rules. Write a recursive rule for, and we begin, this is an arithmetic sequence. It is adding by 10. So that is the common difference. In a recursive rule, we need an initial term. So I'll say that a sub 1 equals 3. We assume the first term is 1 unless told otherwise that it's 0. We're not here, so we're going to say a sub 1 is 3. And then the rule is a sub n. So for any term, you take the term before it, n minus 1, and add 10. We need both equations to represent that sequence. Sequence number B, letter B. Okay, this is definitely geometric, and I would have to take 40 divided by 16 to see that the common ratio is 2.5. Okay, so again, I need to identify an initial term. It's going to be a sub 1 equals 16. Now I'll write the rule. So what you do for any term is you take the term before it and multiply by 2.5. Example 4, translating from explicit rules to recursive rules. So we're given an explicit rule, a sub n equals negative 6 plus 8n. And we're going to need to write that as a recursive rule. It's going to help me if I write out the first few terms of this sequence. So let me throw in 1 for n. So negative 6 plus 8 times 1 is 2. Then negative 6 plus 8 times 2 is 10. And then we get 18. This 8 is the common difference plus 8. Okay, so to review, for a recursive rule, I need to do two things. I need to identify an initial term or two. So I'll do that a sub 1 equals 2. And then I need to write the recursive rule. So for any term, you take the previous term and add 8. Okay, so that's an example of arithmetic. This next one is geometric. Again, I'm going to start with the first few terms in the sequence. So when n is 1, we have negative 3. When n is 2, we have negative 1.5. Right, the common ratio is half, so I'm dividing by half, so this should be negative 0.75. Okay, for the recursive rule, I need two things. I need an initial term or two. A sub 1 equals negative 3. And then I need to say how each term relates to the previous term. So a sub n equals a sub n minus 1 times, and like I said, we are multiplying by 1/2. You might want to rewrite that to 1/2 a sub n minus 1. Just a nicer version of that rule, putting the coefficient in front.